Ready?
Yes.
Ready?
Yes.
Okay, go.
I win!
Oh, I'm a little late, but...
Different ways.
Different, but that was tough. I almost felt like there was no solution for that one. I wonder if there's any games that don't have any solutions.
That sounds like a job for level 314.
Hello, and welcome to Level 314. Today we begin our very first series on solving the Genius Square. Now, don't worry if you're not familiar with the game. It's extraordinarily simple to learn to play, and before we really dig in, I'll give a quick overview. If you're interested in purchasing a copy of the game for yourself, I'll leave a link down in the description where you can do that. And if this, our very first video, gets 100 likes, we'll even give away one free copy to a lucky person. Now, throughout this series, we'll be using a combination of Python and Excel, or your favorite spreadsheet program. And as we dig even deeper into the more intricate parts, we'll be using some C++ as well. And we'll be using these to help teach your computer how to solve the Genius Square. If you're the kind of person who's curious and interested in leveling up in your computer science and mathematics skills, I encourage you to stick around. So, without further ado, let's get started on Part 1, Counting. The Genius Square is reminiscent of a brick-and-mortar Tetris, where two players race to see who can solve a puzzle the quickest. The game is a 6x6 grid of squares, and when starting a new game, you roll a set of 7 dice and place 7 pegs at the positions indicated by the roll. When playing with two players, each gets their own board, pegs, and game pieces. Now, once the pegs are in place, someone will call go, and then the goal is to find a way to fit the 9 colored game pieces shown into the board as quickly as possible without moving the pegs. Pause here if you want to try to solve this game on your own. As you can see, sometimes you'll want to rotate or flip the pieces to make them all fit. Once you're done, you'll just remove the pieces, roll again, and move the pegs to the new positions. There's a wide variety of setups possible, and in fact, the box says there are 62,208 puzzles. That claim is what got me to wondering, is that really the limit? Let's organize our thinking and find out. We'll work out 2 different approaches to the problem. First, a level 5 pi brute force Python algorithm which sets up each game board and counts it, and then in the next video we'll take a more mathematical approach rated at level 10 pi. We'll use the simulated board on the left side of the screen to help visualize what's going on as we build our solution to the counting problem. So let's organize all the pegs into one part of the board so that we can take a systematic approach. Notice that if we're considering solutions to unique games, the pegs have order invariance. That is to say, the game with this board is the same as with this board. We'll commit to keeping the pegs in order from lowest to highest, that way we're sure to only count each game once. Next, let's number the pegs from 0 to 6 instead of 1 to 7. Now there are still 7 pegs in total, but mid and low-level computer languages usually start counting a list at 0, so it will help if we begin the habit of doing likewise. Let's also number the squares again, starting at 0. Okay, but 7 pegs is a lot to think about right now. Let's see if we can make an algorithm to count the games with just 1 peg first and expand from there. We'll use a variable called count to store the number of games, so the first task is to initialize it to 0 with the command count equals 0. Now we'll create a collection of peg positions. There are 4 types of collections built into Python. In this case, we'll use a list. Now right now, a list isn't really necessary since we only have 1 peg, but we'll create one anyway in preparation for when we move to counting the games with more pegs in play. The syntax is important here. The way we tell Python the variable peg is a list is that we set it equal to a list of values surrounded by square brackets. Finally, we initialize variable n, which stores the total number of squares on our game board. Recall our board is a 6x6 grid, which means there are 6 times 6 squares, or 36 total. After the initialization, we set a loop by writing in Python for peg 0 in brackets in parentheses 0, n parentheses. Let's break this down. Peg 0 is the way we indicate the first item in the peg list. Remember, list indexes are 0 base, so the first item is peg 0, the second item is peg 1, etc. Range is what is known as a function, and it returns a range of numbers starting at the first parameter, in this case 0, up to but not including the second parameter. Here our second parameter is n, which has a value of 36. Thus, range returns all whole numbers between 0 and 35. The for loop causes peg 0 to take on the next value in that list each time through the loop. Every time through the loop, when peg 0 moves to a new value, we increase our count variable by 1, thereby counting each game. We do this with the statement count equals count plus 1. To indicate this should occur inside the loop, we simply need to indent it. Finally, we print the value of count using the print function. The way it's currently written, the print would happen each time through the loop. To make it so that the print occurs only once after the for loop has completed, we simply unindent it. Okay, so let's run our program. First, our initializations for count, the peg list, and n occur. Next, we enter the for loop, and our peg goes to the first square, position 0. Then our counter increases from 0 to 1. This is our first game. Next, we loop back up, and peg moves to the next box, box 1. Then our count is incremented again. The peg moves again, the counter increases again, and it continues in that fashion until peg 0 reaches square 35. The count variable increases one last time, and then we exit our for loop because, recall, it continues as long as peg 0 is less than 36, the value of variable n. Outside of our for loop, our print statement executes. As you may have already guessed, in this simple case with one peg, there are 36 possible games. Okay, now let's expand our algorithm to use 2 pegs. First, we modify our peg list so that it can store 2 distinct peg positions. Then we write another for loop to control our second peg and put that loop inside of our first loop. This is called nesting the loops. Peg 1 must start in square 1 because peg 0 is already in square 0. So this time we write for peg 1 in range 1, n. Okay, for one peg there were 36 possible games. Try to make a guess now of how many games there will be with 2 pegs. And let's run our algorithm and see what the answer actually is. First, we initialize a variable count, peg, and n again. Our first for loop gives peg 0 its first value of 0. Then our nested loop gives peg 1 its first value of 1. And finally our count is incremented. We continue on with this internal for loop, moving peg 1 forward as long as it's less than 36, our variable n, and adding 1 to count each time. Let's let it run. And when peg 1 gets to its last value, the problem goes back to the outer loop and increases peg 0 to its next value of 1. But our for loop for peg 1 seems to have a problem. It starts again ranging from 1 to n, but that would put peg 1 in the same square as peg 0, something we know is not possible. We can fix this by coding the range for peg 1 using a variable instead of a hard-coded 1. Notice that peg 1 always starts one place higher than peg 0, so we rewrite the internal loop to be for peg 1 in range peg 0 plus 1, n. Much better. Our board is properly set in the next position, so we increment the variable count and continue as before. Okay, let's fast forward a bit in time. And as we near the end, you might get a hint about one more problem. Notice our outer loop says peg 0 ranges from 0 to values less than n, where n is equal to 36. But peg 0 can never obtain that position since peg 1 will be in the way. Thus, the actual limit for peg 0 is not n, but rather n minus 1, because one peg will always be higher than it is. Fixing that allows our loops to terminate at the right point, and we can print the result. So for one peg, there were 36 possible games, and now with 2 pegs, 630 possible games. It can be quite surprising that adding just one more peg meant that there were almost 600 more games possible. How close was your guess? Armed with what we now know, we can expand the algorithm to the case with 3 pegs. We again expand our list variable peg to hold 3 values. In Python, we can actually replicate a list using the asterisk or multiply symbol. So instead of writing a list with 3 zeros, we can initialize peg by using a list with 1 0 and multiplying it by 3. This comes in handy as the size of our list grows. Our innermost loop, which controls peg 2, is written for peg 2 in range peg 1 plus 1, comma n, because it must always start one higher than peg 1, similar to how peg 1 must start one higher than peg 0. Now we must go back and adjust the range for peg 1 to end at n minus 1, since one peg will always be higher than it is, and adjust the range for peg 0 to end at n minus 2, since now 2 pegs will be higher than it. Okay, let's set the algorithm in motion again. And what's your guess for how many games are possible with 3 pegs? One thing is certain, the counts are starting to get high enough that this simulation is too slow. So let's jump into our Python editor to write the code for all 7 pegs without the overhead of displaying each game in our animation. So, here we are in Spyder, which stands for Scientific Python Development Environment. This is part of the Anaconda toolset. I highly recommend it. It's available for free for use in either Windows, Linux, or Macintosh. I'll put a link in the description, and if needed we can even do a short tutorial on how to get it installed and up and running, but it's pretty straightforward. Our current development environment is broken up into 3 sections. The first is a standard text editor, which you'll be using to edit your different Python programs. Then there's this Python interactive console. Here we can run individual Python commands and even interact with variables or even class objects we've set up in our source code. And finally we have this variable explorer, and here we can see any variables that have been set in memory either through our console or even in programs that we've run here through the editor. So briefly we can actually go ahead and set a variable test is equal to 10, and here in our explorer you can in fact see a singular variable called test. It's an integer and its value is in fact 10. We can do test equals test plus 1, and you can see it now has a value of 11. Okay, what we want to do is open up a new Python program by clicking on this new icon. It gives us some default comments here at the top. It's always good to comment our code. We'll add to these default comments a description of what this program is going to do. So this is our Genius Square game counter. And then we're just going to go ahead and do just as we've done in our experimental program and start setting our initialization of variables. So first we have a variable called count, and we're just going to initialize it to 0. And then we're going to create a list by the name of peg, which is going to be the list of our different peg positions. Remember, Python has 4 different types of collections by default. It has list, tuples, dictionaries, and sets. Lists are very similar to arrays in other programming languages. Finally, we're going to use a variable n to designate the number of squares that are possible. And remember, our board was a 6x6 grid. 6 times 6, we have 36 squares. Now we can go ahead and run this at any time by clicking this green arrow here. Each time we run, it's going to save the program before it runs it, and the first time you run, you've got to give it your own name. So we're going to go ahead and do that and pick a better place to save it. Okay, and we'll call this our gamecounter.py, which is exactly what it does. And you see now it has run our program. Here it says run file and then the name of our file. And in our Explorer, you can in fact see the values of the various variables we've initialized with our program so far. You can even interact with them, so we can say n equals n plus 1. This is, of course, is changing the number of grids, the number of squares on our board. We don't typically want to do that, but you can see it does change the value here. Another thing that's good to experiment and get used to using zero-based index for our lists. So if we want to change this first value here, we have to set the value of peg 0. It may be sort of counterintuitive to you, but people who are used to using C or C++, you're used to this, and we're going to get used to it as we use Python more and more. So we'll go ahead and set the first value to 10, and you can see right here in our Explorer it is in fact set. We'll set the value of the 5th square, or peg 4. We'll just call that 314. And you can see here it in fact has that value. Notice here if we run again, it runs our program starting from the beginning, and it has reinitialized all of our variables just as we'd expect it to. So all that's left to do now is to go ahead and do our nested for loops, which will count through all of the values it'll work through all of the ranges rather for our pegs. So the first peg is going to work through a range starting from 0 to n minus 6. One note here on an abbreviation, if you will. Range will assume that 0 is the first value in your range, so if you don't put it, this is the same thing as doing 0 comma n minus 6, and that's what we'll do here. So then we do our second peg for peg 1 in range, and now as we do the remainder of the pegs, remember it's got to start at the peg just before it plus 1, so we always start 1 higher than peg 1, and this is going to end now not at n minus 6 but n minus 5, and each time that will get lower. And we'll continue on through the rest of the pegs. On this last peg we could do n minus 0. There's no need for it though, so just for brevity's sake we'll just do n because n minus 0 is of course n. And as we look over our loop, important to note that each time we indent one more time. So that means this loop is inside of this loop. This loop here is inside both this loop and this loop, etc. on down the list. Also important to check to make sure that each time we've started just to the right of the peg or just one more than the peg just before us. So peg 2 is peg 1 plus 1, peg 5 is peg 4 plus 1, etc. And each time this n should be stopping one higher than the one before it. So this is n minus 5, this one stops, n minus 4, 3, 2, 1, and finally our final peg stops at n. In our innermost for loop, we've got to increment our count variable, and we can do that by count equals count plus 1. For an optimization, we can also rewrite this to count plus equals 1. This is the same, it's equivalent to count equals count plus 1. Just as we're optimizing code, this is one of the things we can do. We'll talk about optimization a little bit further in, but this is one that we can do very early on, so we will do it. And that's it. So our nested loop is done. All that would be left to do is to go ahead and print our results. And I'm going to do something a little bit fancy here. You don't have to worry too much about it, but I'm going to format our output. We'll do that using the format of strings command, and This particular format that I'm using will print the string game count, and then it will print our number count, but with commas separating in the thousandths place. So we're about to run it. This is your last chance to guess, if you'd like to do it, of exactly how many games are possible when we use all 7 pegs. Here we go. And our code runs in just a matter of a second or two, which is great, and it does give us an answer. So using all 7 pegs, there are 8,347,680 possible games. And it's great here in our variable explorer, we can see some important things that our n, the number of squares, doesn't change throughout the program. This is exactly what we would expect because our number of squares is the same. Our count does in fact have our final value of over 8 million games possible. And really great to see is our peg list. And we can see, if you remember in our visualization earlier, at the end we would have 2 pegs at the end. This time we have 7. The seventh peg is in square ID 35. Remember, these are 0-based indexes, so 35 is actually the 36th square. The 6th peg is one to the left of that, and the next is left of that, etc. on down the list. We can see our peg list ended just as we'd expect it to. This gives us some confidence in our result. It might be a little bit surprising, but there are many games, well over 8 million. Really too much for you to play them one at a time manually. So this really confirms that if we really want to explore all these games, it's best if we write some code to do it. And there you have it. The box says 62,208 games, but in reality, using all 7 pegs, there are over 8 million games. And in fact, there are even more games if we choose not to use all 7 pegs. So why does the box have a discrepancy between what we calculated? And how do we figure out if our answer is right? And if there are more games, how do we figure those out? Well, we'll figure that all out next week as we take a more mathematical approach. And just as a hint of how we'll be doing that, we'll be using this rare mathematical symbol. So if you've liked what you've seen and if you've learned something, please hit the like button. If you're interested in how this all turns out, stay tuned by clicking on the subscribe and ringing the bell. So until we meet again, keep taming irrationality bit by bit.